Welcome back to the last lecture in this series on an introduction to graph theory. So today we'll be talking about a problem from the movie Good Will Hunting. If you haven't seen this movie, I highly recommend it. I think it's really good, especially if you like math. And in this movie, there's a professor at MIT who posts some problems on a blackboard out in the hallway at MIT. And he says that these problems took him and his colleague 2 years to solve. Now, Will Hunting, who was a janitor at MIT, sees the problems and solves them on the blackboard, or he starts to, before the professor sees him, and then he runs away. So I thought it'd be fun today to solve one of these problems. And the problem that's listed on the blackboard is to draw all homeomorphically irreducible trees with n equals 10. So with 10 vertices. So let's unpack what this is saying before we can try to solve it. So first we'll talk about something called a tree. So let's review that a walk is a set of distinct edges that we can trace in the graph without picking up our pencils. A path is a walk that doesn't go through any vertex twice. And a cycle is a path that starts and ends at the same vertex. And a graph is connected if there is a walk between each pair of vertices. So the graph isn't split into disjoint pieces, it's all connected. So then a tree, this is a new definition, is a connected graph with no cycles. So let's look at these three graphs here and decide if they're trees and explain why or why not. So pause the video and think about that on your own. Okay, so are these graphs trees? Well, let's look at this first one. So we need this to be a connected graph with no cycles. Well, this is not a tree because it's not connected. Let's look at this next one here. So this is connected. There's a walk between every pair of vertices. And there are also no cycles. We don't have any like loops in this graph. So yes, this is a tree. And now let's look at this last graph. It is connected, okay, but there is a cycle. We have this triangle right here, so this is not a tree. Okay, so we have this theorem about trees. So if we let G be a connected graph, then the following statements are equivalent. So what that means is if one of these is true, all of them are true. So the first one is G is a tree, so connected graph with no cycles. The second one is there is a unique path between any pair of vertices V and W in G. Okay, and we can think about why a cycle would prevent that from happening. If we look at the triangle part of this graph here, if we look at a path from, let's say, this vertex to this one, we can go along this edge, or we can go along these two edges. And these are not, so there's not a unique path between these two vertices. So that's something that would tell you G is not a tree. And then the last statement is that G is minimally connected. And what that means is if we remove any edge of G, we will disconnect it. Our graph will no longer be connected. Okay, so if we have a tree, we can pick one vertex to be the root. We'll call this a rooted tree, and we can redraw the tree in a way that I'll show you. So we pick any of these vertices to be our root. Let's say we pick this one. Then we can draw this tree in the following way. We put our root at the top, okay? And then we're going to have levels of this rooted tree. So at this top level here is our root. Then on the next level, we're going to draw all the vertices that are a distance of one edge away from that root. So we have 1, 2, 3, 4, 5, 6, 7, 8 of them. Okay, so we draw our 8 vertices down here on the second level. Okay, and connect them with the edges that are there in that graph. And this is just a nice way of drawing the rooted tree. It makes it more organized. Now we could have picked another vertex to be our root. Let me just erase this one. Okay, let's say we pick this vertex to be our root. Then we'll put that at the top here. And then on the next level will be all of the vertices that are a distance of one edge away from it. So there's only one of them, it's this middle vertex here. So that's on our next level. We connect them with the edge that's there in the graph. And then on the next level is the vertices that are a distance of one edge away from this one. Okay, so we have 7 of them. Okay, and we connect them with the edges that are there in the graph. Okay. So that's a rooted tree. So thinking about rooted trees, we can answer this question. How many edges does a tree with n vertices have? So maybe pause the video and think about that for a minute. Think about what rooted trees look like and how you can think of the edges in an organized way there. Okay, so how many edges does a tree with n vertices have? Well, if we draw it as a rooted tree, okay, then we can think about it in this way. Each vertex has exactly one edge that is directly above it. Okay, so that's true for all of the vertices except for the root. Since there are n vertices, there are n minus 1 vertices that have an edge directly above them. So that means we have n minus 1 edges. So there are n minus 1 edges in a tree with n vertices. This can be seen by looking at the rooted tree, which has one edge above or directly above each vertex, except for the root. Okay, and then we say, last part of our the definition for the question we asked at the beginning is homeomorphically irreducible. So a tree is homeomorphically irreducible if there's no vertex of degree 2. So there's no vertex with exactly 2 edges coming out of it. So before we can go to answer our question, we need to learn about graph isomorphisms. So we say 2 graphs, G1 and G2, are isomorphic, so they're isomorphic to each other, if their vertices can be labeled so that for any 2 vertices V and W are adjacent in G1, if and only if they're adjacent in G2. Okay, so what does this mean? We can think of this as moving around the vertices of the graph in a way that we just like stretch and move around the edges without breaking any of the edges. So we get another graph that's basically the same as the first one. Oops, sorry about that. Okay, so where does this idea come from? Let's think about this graph that I'm drawing here. What if I draw another graph that looks like this? Okay, what's the difference between these 2 graphs? Well, basically these edges on the end are just pulled out more in this bottom graph. So we would want to say these graphs are the same essentially. So this is the idea of isomorphic. These 2 graphs we want to say are isomorphic to each other. In fact, they are isomorphic to each other. So let's do this example. Are these graphs isomorphic to each other? So in order to show that they are, we want to label the vertices. We have 4 of them, so we can label them with A, B, C, and D, so that 2 vertices are adjacent in the first graph, if and only if they're adjacent in the second graph. So pause the video and either try to come up with a labeling or explain why there isn't one. Okay, so it turns out there is a labeling for this graph. You want to think about which vertices in this graph are basically the same as ones here. We could think about which vertices are connected to the other ones. So let's just start by labeling this vertex here A. And we'd want to find vertex A in this second graph. Okay, so vertex A has degree 3, so we want to find a vertex of degree 3 here, because anytime this is adjacent to any other vertex, it has to be adjacent to those same vertices in this graph. Okay, so this vertex is degree 3. This graph is symmetric, so it doesn't matter if we pick this one or this one. So I'm just going to pick this one. Okay, now let's label this vertex B. It's adjacent to A, and it has degree 2. So we need a vertex here that's adjacent to A and degree 2. And we can pick this one. So then we'll label this vertex C. It's adjacent to A and B, and it has degree 3. So which vertex of this is that true for? It's true for this one here. So then this vertex has to be labeled D. It's adjacent to A and C and has degree 2. And this vertex here is adjacent to A and C and has degree 2. So we'll label this D, and this shows that these two graphs are isomorphic. So yes. Now, are these two graphs isomorphic? Pause the video and think about that. Okay, so let's look at these two graphs. If we wanted to start by trying to label, before we just go ahead and do that, we want to look at the degrees of the vertices. Because if we want to preserve adjacency in our labeling of the graph, the degrees have to be the same. There has to be the same number of vertices that are adjacent to the vertex we're looking at here if we're going to label that vertex with the same label in this graph. So I noticed that this vertex here has degree 3, but there's no vertex here with degree 3. So no, these graphs can't be isomorphic. So the degree is really important in looking at graph isomorphisms. So that leads us to define something called the degree sequence of a graph G with n vertices. It's a list of the degrees of the vertices. So if we say the degrees are d1, d2, all the way through dn, we need n of them because there are n vertices. And we order them this way, where d1 is greater than or equal to d2, which is greater than or equal to d3, and the least one is dn at the end. Okay, so we want to write them so that we have a non-increasing sequence. So let's write down the degree sequence for the two graphs in the previous example. You can pause and try that first if you think you know how to do it. Okay, so let's look here. So we want to list the degrees of the vertices, starting with the highest degree and ending with the lowest, and going in order. So in this graph, we have a vertex of degree 3. We have two vertices of degree 2 and a vertex of degree 1. So our degree sequence will be 3, 2, 2, 1. Then for this second graph, we have a vertex of degree 1, vertex of degree 2, and degree 1. And we need to go in non-increasing order. So our degree sequence is 2, 2, 2, 1. Or sorry, 2, 2, 1, 1. Okay, so something that follows from what we talked about when we were looking at this previous example is that if two graphs do not have the same degree sequence, they are not isomorphic. This makes sense because we want to preserve adjacency in the graphs when we're seeing if they're isomorphic to each other. So if, for example, we don't have 3 vertices of degree 3 in both graphs, then we won't be able to label the vertices in a way that shows they're isomorphic. Okay, so let's go back to our problem and let's restate it. We want to draw all homeomorphically irreducible. So remember that means we don't have any vertices of degree 2. We want trees, so we want connected graphs with no cycles, with 10 vertices, and we want to do this up to isomorphism. What does that mean? It means we don't want to like double count graphs that are isomorphic to each other. So if we've already drawn this graph, we don't want to also include this graph because these are isomorphic to each other. Okay. So now you have enough tools to solve the problem if I tell you that there are 10 answers. So try to write those down. It might take you a little while. And I will skip ahead in the video and write down all of mine. Okay, welcome back. So here are all 10 graphs. You probably want to pause the video and make sure you have all of these. It's really easy when you're doing this to write down 2 graphs that don't seem like they're isomorphic, but they actually are. So it might take you some time to see that what you've written down, those graphs are isomorphic to all of these. You probably haven't written down the graphs exactly in the same way I did. And make sure you don't have graphs that are isomorphic to each other. Okay, so something to note about the movie is that Will Hunting wrote down these answers on the chalkboard, and actually he didn't finish. He only wrote down 8 of the 10 before he was caught and had to run away. But he didn't do what's the most important part, I think, in math, and that is prove that these are the correct answers and that there aren't any more of them. Okay, so getting the answer is not useful unless you've proven that it's correct. Okay, so how can we do that? Well, we can prove our answer is correct, and what I mean by that is none of our graphs are isomorphic to each other, and there aren't any more than 10 by looking at degree sequences. So let's think back to the degree sum theorem, or the handshaking theorem from our first lecture. And what did it say about the sum of all of the degrees of the vertices? Okay, so it says that the sum of the degrees of the vertices is equal to 2 times the number of edges. Right, so how many edges do we have? Well, in all of our answers, we have 10 vertices. And remember earlier in this lecture, we said that a tree on n vertices has n-1 edges. So that means we have 9 edges. And the degree sum theorem says that the sum of the degrees of the vertices is 2 times the number of edges. So in this case, it's 2 times 9, which is 18. So what that means is if we have a degree sequence, then the sum of all of the degrees in that sequence has to add up to 18. Okay, next, since trees are connected graphs, what is the minimum degree of a vertex in any answer to the problem? So since the trees are connected, we can't have any vertices just floating there by themselves. They have to be adjacent to some other vertex. They have to be connected to an edge. Okay, so the minimum degree of any vertex is 1. Can't have a vertex of degree 0 in a connected graph. And what's the maximum degree of any vertex in an answer to the problem? Well, we're just looking at simple graphs here, meaning we don't have any loops and we don't have any double edges. Okay, so let's think about a single vertex in the answer. The maximum number of edges it can have is the number of remaining vertices. So that vertex could be adjacent to all 9 of the other vertices, and that vertex would then have degree 9. So now I want you to write down all possible degree sequences for answers to the problem. And remember that we wanted these graphs to be homeomorphically irreducible, meaning none of the vertices have degree 2. Okay, so we can't have any 2's in our degree sequence. So you can either pause and do that on your own right away, or I can help you with the first one. So we want a degree sequence, so we want to write down all 10 degrees of the vertices, 9, 10, where the maximum degree of a vertex is here, the minimum degree is here, and this sequence is non-increasing. Okay, so let's start with the maximum possible degree of any vertex, which is 9. Now remember, from the degree sum theorem, the sums of all of these entries in our sequence will be 18. So we have a total of 9 left to distribute to these slots, and there are 9 slots. Each one has to be at least 1, so they all have to be 1. Okay, so that's our first degree sequence. So why don't you write down all the rest of the possible ones, and I'll fast forward the video and show you my answers. Okay, so these are all possible degree sequences. Remember, we can't have any with 2's in them. So the last thing I want you to do is to go through each degree sequence and reason why there are no other trees with that degree sequence besides the one you drew for your answer. And for a lot of these, it might help to draw them as rooted trees. So I'll let you do most of them, but I'll talk through a couple of them with you. Let's start with this first degree sequence. What this means is we'll have one vertex of degree 9, and all other vertices will have degree 1. So let's draw out our 10 vertices. Forget to count. 6, 7, 8, 9, 10. Okay, so one vertex has degree 9. That means it's adjacent to all of the other vertices. There's only one way to connect this vertex to all of the other vertices. And once we've done that, all the other vertices have degree 1. So there's nothing left to do, and there was only one way to make a graph like this. So you can check to see which one of yours this is isomorphic to. And we've just reasoned why there can only be 1 with this degree sequence. Now let's do a harder one. Let's say 4, 4, 3, and then the rest are 1s. This degree sequence has multiple answers to our problem. Okay, so let's think through what they are and why there aren't any others. So it's helpful to draw this as a rooted tree. So remember, we want one root at the top. Then the next level is all of the vertices that are a distance of 1 edge away from our root. Then the level after that is all the vertices a distance of 1 edge away from those. And we connect them, these levels, with the edges that are in our graph. So what can we do? There are a few things we can do to start this. Let me redraw that over here so we have more space. Let's say we start the root with, choose the root to be a vertex of degree 4. Okay, then what can we do? Well, we can make this one have degree 4. And then where do we want our vertex of degree 3? Well, we could add it onto here. And notice if I chose like this vertex instead of this one to attach all of these other edges onto, these two graphs would be isomorphic. Okay, it doesn't matter which one we choose to attach these onto. Okay, so here's one answer to our problem. Let's see what the others can be. Okay, so we've done 4 on this level, degree 4 on this level, degree 4 on this level, and then, whoops, degree 3 on this level. What else can we do? Well, we can start with degree 4 again. Okay, and then we could do degree 3 next, and then attach to that degree 4. Okay, and we can ask ourselves, are these two graphs isomorphic? Okay, and you can think about that for a while. The answer is no, they're not isomorphic, and you can use a degree argument. So notice in this tree here, we have a vertex of degree 3, which is adjacent to both, oh my gosh, I drew too many edges here again, which is adjacent to both vertices of degree 4. But in this graph, our vertex of degree 3 is only adjacent to one of the vertices of degree 4. So they're not isomorphic. Okay, and then anything else you can do, so we've already done starting with 4. Well, we can start with 4 and then write down this tree. So we have degree 4 coming off of here, and then degree 3 coming off of, let's say, here. Okay, and I claim that this tree is isomorphic to one of these. And which one is it? Well, let's think about that for a minute. So we have, let's see, this is the one where the vertex of degree 3 is only adjacent to one vertex of degree 4. So that's this tree right here. Okay, and you can pick a labeling of the vertices that shows they're isomorphic. Right, so that one's the same as what we wrote down already. We could write down others. We could say start with a vertex of degree 1 and then do all of this. So degree 4, degree 4, degree 3. Okay, but you can see pretty quickly by thinking about moving this vertex down, pulling it down here, pulling that edge down so that this vertex is on this level now, that this graph is isomorphic to the first one also. Okay, and you can keep making these arguments to show that these are the only two trees with this degree sequence that satisfy the conditions we specified for this problem. You could do that for all of the degree sequences and prove, unlike will hunting, that you've actually solved the problem. Okay, so I hope you've enjoyed these lectures. And yeah, let me know in the comments if you have any questions.